Mike just gave us this conceptual discussion of what is a downstream assessment. And this is, and coming from an engineer that performs downstream assessments, this is a huge help in actually doing them, is if you understand the concept. If you understand, well, why am I even doing this, and you know what to look for in the end result. And so focus on that. Focus on, when you're trying to develop this knowledge of how to review or how to perform them, make sure you know what your end result is going to be, or it needs to be. So I just want to talk to you. We've developed 4 steps to actually performing these downstream assessments, and I know a lot of you guys in here are probably not so concerned with actually performing them, but more so reviewing them. And we kind of feel that if you know how to perform them, you're going to really know how to review them. So this applies to both performing and reviewing. The first step we want to look at is determining your limits of downstream assessment. And we talk about downstream assessment all the time, but not everybody knows how far do we look downstream. Do we look, the extreme is the Gulf of Mexico? Do we look that far downstream, or do we look just at our discharge point of our site? Or how do we define how far we really need to look downstream? So we're going to clear that air and really give you some tools to calculate that point. The next step is the data collection. Once you know really what your downstream limits are, so let's figure out what's going on within this watershed. Like Mike said, let's figure out problems. Let's figure out if there's any models available. Let's get our hydrologic parameters defined and those kind of things. And then from there we'll move on to really performing the hydrologic analysis and step by step through HMS or through a software, trying to determine what impacts does this one site and this one development truly have on the watershed. And then finally we'll get to the what do we do with it? We have this information now. What is our end result going to be, and what do we really want the outcome of this, our findings to be? So to determine the downstream limit of your assessment, ISWIM defines 2 different methods to determine this downstream limit. The first one is called an adequate outfall, and now just reading the definition, it's defined as a location of an acceptable outfall that does not create adverse flooding or erosion conditions downstream. It's a very generic description, and it's a very generic, well, what is adequate? That's probably subjective, what is actually adequate. But we'll define what that is a little bit in just a minute. And then the second method is the zone of influence. And this is an actual way to calculate a point downstream where your proposed development no longer has a significant impact on the receiving stream. So we'll go through a couple examples of how to define that, how to calculate the zone of influence. So an adequate outfall is, you see underlined at the top there, it's adoptee defined. And so like I said, it's a subjective process. What is an adequate outfall? I could probably ask each person in this room and we'd come up with different answers for what is adequate to outfall into and to be a downstream limit of our assessment. So it's important to note that when you're performing these, or if you're a city and you've adopted ISWIM, you've defined what adequate outfalls are for your city. But a lot of times what we'll see is FEMA floodplains. A lot of times we'll have, we'll have defined existing systems that were designed and built for ultimate conditions, so those will be known up front. Or define natural channels, waters of the U.S., and there's whatever the city decides at that point is acceptable and adequate for an outfall. But the key down there to note is we're really looking for a point where we're not causing any negative impacts from our discharge point downstream, wherever that is, however far that reaches. We just want to find what that point is, and that's the change in philosophy we're talking about. The second method, like I said, is called the zone of influence, and this is defined in ISWIM. And if you want to go back and read the material, like Mike said, it's in the hydrology technical manual of ISWIM. But the zone of influence works on the 10% rule. 10% rule basically says we're looking for a point on the receiving system downstream from our site where our site only comprises 10% of the entire drainage area at that point. So we get a lot of confusion on this, what the zone of influence is. What are you talking about, 10% rule? It's simply, if your site is 10 acres, then you have to look downstream to a point in your downstream assessment where the total drainage area is 100 acres. So your site is 10% of the entire drainage area. As simple as that. Important to note, and you'll find this in ISWIM as well, 10% is obviously just an estimate. It's not cookie cutter. It's not going to be exactly the same for every time, but usually 10% is a pretty conservative estimate for looking downstream. But there will be the occasion where maybe it's not far enough, and we'll find that out in a later step. So we'll go through a couple examples. We'll look at the same little illustration that we had before of this proposed development that happens on Tributary 1. It's 30 acres in size, and these are all arbitrary numbers that are made for illustration, so don't get your scale out and measure and call me out or anything. But we've got a 30-acre development, and we're kind of on the midpoint of the Tributary 1 watershed, but we're pretty far upstream in the entire watershed down, to our confluence. So if we look at that 30 acres compared to our 10% rule, we're looking at a total drainage area of 300 acres is where our downstream assessment can stop. So if you look downstream, there's a 300-acre point just before the confluence, and that is the point to which, from the discharge point of your proposed site, you have to evaluate the change in drainage and the increases in flow rate or velocity for that entire stretch, not just for that downstream point, but for various design points throughout that zone of influence to determine if any adverse impacts are occurring. So to look at the same example, but we'll move the development maybe downstream in the watershed after the confluence. Kind of want to show you guys the difference that it makes and based on where your proposed site is placed within a watershed. If you're upstream in the watershed like we are in this first development, and you're right up next to the stream, typically your zone of influence is going to extend a little ways down because your site is a larger percentage of the drainage area to that point. But you go downstream and we look at that same 30 acres, moved past the confluence, now we have all the drainage area from Tributary 2 as well to count at this point on the receiving stream. So right at the discharge site of our proposed, or the discharge point of our proposed site, the total drainage area is 1,000 acres. And so you're seeing now that instead of a 10% rule and also stretching downstream to our point of influence, or our downstream point of influence, now we're actually at a 3%. And so our flow, or any increases in flow we have from our site, are going to be a lot less significant to the total drainage area at that point. If y'all have any questions on this, it may be very simple to some, it may be confusing to others. Just feel free to ask any questions you might have. One last example that I want to go through. It's kind of a real life example on a project. We've got a Tributary 1 and then the main river at the confluence down on the lower right hand side. We have a proposed 23-acre site offset a little ways from Tributary 1 to the west there. And then a discharge pipe system, an existing system that the proposed 23-acre site is discharging flow from the site out to the Tributary 1. Now this pipe system outfalls at a point, and sorry this font is a little small, it was a GIS exhibit and doesn't really blow up that well, but the total drainage area at the downstream end of that pipe, once you hit that confluence with the stream, is 646 acres. Just before the outfall in that pipe, the total drainage area is 105 acres. Just take a mental note of these areas, and then obviously at the upstream portion of the pipe, right before the site discharges, the total drainage area is the drainage area of the site, which is 23 acres. And then we look a little bit further downstream, and our total drainage area at the confluence, right before the confluence on Tributary 1, is 839 acres. So with that being said, does anybody want to venture a risky guess to determine what potentially would be the downstream limit of the zone of influence on this site?
Right where the 600, whatever you said, acres is at the end of the pipe.
Okay, 646 acres. Anybody disagree with that? Yes, sir.
Since you're proposing a pipe there to pipe that stuff?
Well, I was just saying, hypothetically, it's an existing pipe.
Is that an existing pipe that you're bringing it in?
Yeah.
Or existing? But if it's proposed pipe, I'd say you take the 103 acres at the outflow of that pipe.
Well, I think if it was a proposed pipe, we'd call the downstream end of that pipe our discharge point, and that would be the start of our zone of influence, and then we'd have to look downstream from there.
I mean, it could be more than 6, 4 to 6.
Okay. Well, for this basic example, assuming that it's an existing pipe and our discharge point is right here where that pipe starts, for this example, I'm determined that the zone of influence ends at the confluence with tributary 1. So at 646 acres, we're looking at, for the 10% rule, we're looking to find a point where the drainage area is 230 acres. And at the confluence, we're looking at 646. And so we're well below that 10% mark. Pretty sure that at that point, we're not going to have a very significant impact on the entire watershed of 646 acres. Now the other option, the other thing you can look at, we'll show you the point there, but if you had a larger site and that 90 acres or something, and at this point, right before the confluence with the river, you're at 839 acres. Well, your 10% rule is not necessarily going to cover you at that if you have a 90-acre site. And so you'd need to look at the total drainage area of the river, which in a lot of cases is you're looking at not acres anymore, but you're looking at square miles. And so it's a very insignificant amount of flow at that confluence. Any questions on that before we move on? This is kind of, in my opinion, the foundation of doing a downstream assessment, is really defining this point and being confident in it. Awesome. So the next step, once we determine that downstream point, we're looking at data collection and trying to absorb as much and research as much information as possible from our site to the downstream limit of our zone of influence. So we want to find out what's really going on out there. Are there any existing problems? Maybe we have this zone of influence and maybe we're not increasing the flow rate that much, but maybe there's a huge flooding problem that we need to find out about before we go develop. So we'll collect that. We'll collect all of the necessary hydrologic parameters, the topography, collect your soil data, plans for existing infrastructure that's already been built. That's a very important one to find out what kind of capacity you already have out there, if there's been any city improvements done on the channel you're discharging into. That's a pretty important component. If it was designed for ultimate conditions, then you're pretty much good to go at that point if you find that out. So then, FEMA floodplains, future land use. You'll hear us say future land use for the entire watershed, because that's what we're designing, or we're assuming is the case in these downstream assessments. Rainfall data, which can be found in ISWIM, and then finally existing models. And you heard Mike say that, talking about the cost of downstream assessments, the cost goes down tremendously when you have an existing hydrologic model available for your receiving stream. So, that existing model is a really important thing you want to look for. It's something you want to find. It's a gold mine if you find it. Typically, if you're discharging into a large river or your site is located within a pretty significant watershed, then you're going to be able to find some sort of hydrologic model. So at that point, the step is just verifying that model and figuring out what's going on inside the model instead of just starting from scratch. So at this point, you see the stop sign. If you're lucky enough, then potentially you can stop at this point. Like I said, if you find out that to the point of your downstream limit of your zone of influence, if you find out that everything between your discharge point and that zone of influence has been designed and built for ultimate conditions, then that assumes that your site was planned to be built out and it was planned for in that infrastructure. And at that point, if you find that to be the case, you stop, write a memo, discuss it with the city, and that's that. Doesn't always work out like that. As we found out, most of the time it doesn't work like that. And so we continue on to the next step, which is the hydrologic analysis. So we're talking about hydrologic analysis, but we've got two different components of this. The first one is the watershed, and this is probably the one that trips the most people up if there's not a model available is, well, how am I going to calculate, I've got a 1,000-acre watershed. How do you expect me to do that for $10,000 to, figure out the hydrologic capability or the hydrologic results of this watershed? But we'll kind of show you how to define that. And then the site hydrology is the next important thing. So the site hydrology is what's actually changing in your model. So in the end, in this downstream assessment, you're going to have an existing model and a proposed model. And the proposed model will only be a modification to your site. We'll change from existing to proposed. I've got a note down there saying if the hydrologic model is available for the watershed, that's not the end. You don't just plug change your number in there and that's it. There is a little bit extra work that goes into breaking up basins and making it truly match the characteristics of where your site is located. Typically, if you look at this example on the right, the figure on top is that watershed we just used in our last example. And it's a single basin watershed and it goes down to the confluence with that main river. Well, in our case, our zone of influence is located upstream from that confluence. So we're not accounting for all of that flow. We're also going to peak a little bit sooner than the existing model is showing to peak. So what we'd want to do is take the parameters that are in there in the existing model, modify those using simple ISWIM hydrology techniques, and update the numbers for the watershed, and then we'll add a basin in for our existing site. And so that's the modification that would be required if the model is truly available.
You're saying that you'll break out a little area for your site,
Right.
undeveloped.
Undeveloped.
And then you can model it with it developed and see what
Right.
happens. So you're talking about HMS.
HEC HMS is that's what we use for all these downstream assessment. I think that's pretty much the industry standard for especially simple hydrology, basin hydrology like this. I think that's pretty standard. I haven't done a downstream assessment in anything else, but it for sure can be done.
And the reason you're having to do a HEC 1, HEC HMS is it's all about the timing. And if you're doing the rational method, that's not capturing that timing. You're really concerned about the timing.
Okay, so we just finished talking about, if we have an existing model available. In some cases, we don't have a model available, and that's the case where we do have to calculate and, model this whole system from scratch. So we, like we were talking about, and the discussion was we calculate this on fully developed, and that's what we're recommending based on this first come, first serve basis we were talking about, and to make sure that everybody's on the same playing field as this entire watershed develops over time. So we'll calculate our curve numbers using future land use, soil, typical hydrologic principles defined in ISWIM. We're not going to go through the actual process of calculating those today. And then, like we've been saying, time of concentration, and this is one of the huge things, and probably the most important aspect of downstream assessments is really determining and nailing down what your timing is from your site to the peak flow of the watershed. And so this step right here, calculating your time of concentration, not only for your watershed, but also for your, and there's a little example of that, but also for your proposed site, time of concentration. Those are very crucial components to get right and to take a lot of care in figuring out. So I've got a note down here that says the most important component of a downstream assessment, obviously, this is probably obvious to all of us, but really accurately representing the change from existing to proposed. We can change some numbers, we can lower the time of concentration by 5 minutes or do something arbitrary, but we want to make sure we're doing it accurate. Otherwise, like Mike was saying, the cumulative effect of a lot of small errors in a watershed creates flooding problems that we see now. So make sure that you're taking care and calculating that time of concentration well, just calculating your change from existing to proposed. Okay, so like I said, we'll have two models at the end of this, and one's existing conditions, one's proposed conditions. Using all of your, we did this one very simply. I don't know that I even ran this model. It was more for a diagram, but very simply to show, what our basin model, how simple this basin model is. Excuse me. So what we'll enter is fully developed watershed conditions for the entire watershed, parameters that we just got done calculating in the last step. And then we'll enter our existing conditions parameters for the proposed site. Run that model, and then copy it, create a new model exactly the same, and then you're changing existing conditions on your proposed site, and all you're changing is that to proposed conditions or ultimate conditions on that site. So that's the simple change, and we can have discussions, I guess, about what the best methodology to go in and do that, or the best calculations to find that. But we're trying to keep this method simple. And ISWIM defines 3 storm events: the stream bank protection, conveyance, and the flood control or flood mitigation storms. And these are different. The stream bank protection is obviously a smaller storm. Conveyance is usually mid-range, and then the flood protection is, I think, always 100-year. I don't know if anybody's ever done differently, but those are the 3 storms that you run for existing and proposed, and you analyze the impacts in all 3 of those storms from existing to proposed. And that's for your entire zone of influence, from your discharge point of your site to your downstream limit that we calculated in option or step 1. Are there any questions on this before? Any additional questions? Okay. So just a quick summary. I'll calculate the basin parameters for the ultimate and the watershed, existing and proposed site, create a hydrologic model, and then create an ultimate hydrologic model. Then we'll just compare the results from existing to proposed. So, like I said earlier, the zone of influence 10% rule is not always accurate. It's not always enough. And there, ISWIM gives an instruction to make this an iterative procedure if you find that there at your downstream limit you are finding increases. So the idea is that maybe there's increases within the zone of influence, but you want to find however far you need to reach downstream, you want to find that point where there is no longer an increase in your system. If you find that's the case, post-development Q is greater than pre-development Q, or if you're finding an increase in velocity, so even if you decrease the flow, maybe something's changed downstream and you're increasing the velocity. And the allowable velocities are shown in the hydraulics manual. But if that's the case, then ISWIM provides instruction to reiterate this procedure and find out and extend your model downstream to find out how far you have to go. And sometimes this takes a few iterations. Sometimes it's very quick to figure out if you have to go past that 10%. But it's just want to make the point that it's not always 10% is not always an exact estimate. It's not always a conservative estimate. Sometimes, like we were discussing earlier, maybe it's not enough. Okay, moving on to the final step, and this is where we figure out what to do now. We're going to determine based on results what our required action is. 2 outcomes. Obviously, we could have no increase at all throughout the entire zone of influence, and from that, no action besides documenting that is required. But most of the time, we're going to have an increase in, not most of the time, some of the time, we're going to have an increase in flow rate or velocity caused by our proposed site. And so at that point, ISWIM defines 3 options to mitigate that increase. And so you can see these options in the technical manual in the handout that we gave you. The first option is what we said at the end of data collection, where we said if you find out that everything in your zone of influence is capable of handling your increases, was designed for ultimate conditions, and that's really the key. It was designed to handle you after you developed. You document that and move on. If that's not the case, then the other 2 options are, you reduce the water surface elevation. So you find a way, maybe downstream, to do some channel improvements, or to increase the conveyance or the armoring of the channel bank downstream. And then finally, design on-site structural controls to maintain pre-development flows. So that's a little bit more familiar. but it's not just as cut and dry as maintaining 100-year pre-development flow. There are requirements for stream bank protection for the smaller storms to make sure that we're not releasing more than previously in a 2-year storm. Okay, and finally, this is where it all comes together. This is the most important part of this entire thing, is figuring out and having a meeting, developers, engineers, cities, to determine where do we actually go from here. And so engineer will submit a memo and documentation stating the findings of this assessment. Usually we recommend this to happen soon in the development process, because obviously if you got somebody coming in that, you know, they're not going to want to build detention if they don't have to, and they're going to want to use that land to make money if they can. So if you find that out sooner than later, you're going to save a lot of money in the long run. And with that, I'll turn it over to Mike and he'll go through some examples.